Professor, you're on mute right now.
All right. Shoot. Okay, so I guess I was talking for a while on mute. Okay, now I'm off mute, and so let's go back and let me back up and talk about what I was talking about. Okay, so once we get a black precipitate over here, then that's a positive for silver ions present in our mixture. And so what we're going to do next is we're going to test for barium, lead, and manganese. And so this step here, this step is called the separation step. This separation step is critical here, okay, for a couple of reasons. One, we need to make sure we precipitate out all the silver ion here. Because if we don't precipitate all the silver ion, then some silver ion will leak over here. And not only will we have lead, barium, and manganese, but we'll also have some residual silver ion. Well, having residual silver ion over here is going to be a problem because in the next step, we get rid of the lead. How do we get rid of the lead? Well, we add iodide in the form of potassium iodide. So lead ions like iodide ions. Lead ions and iodide ions, they like each other and they'll precipitate PbI2. What other ions does iodide like? Well, iodides, you know, chlorides, bromides, and iodides are all soluble. So they don't really like barium. Barium iodide soluble, manganese 2 iodide is soluble, except for silver, lead, and mercury, lead 2 and mercury 1. And so if there's silver ions present, what will happen is we'll get a precipitate here too. And what that can lead to is something called a false positive. So if silver ions, if we didn't get rid of all of the silver over here, then some of the silver leaks over here. If some of the silver leaks over here, then the silver will react with the iodide, and that could potentially give us a precipitate. And so we might not have any lead here, but we get a precipitate and we get a false positive for lead because we got a precipitate just because the silver leaked through. You know? Silver gives a yellowish precipitate as well. And so we have to be very careful in this separation because that could lead to false positives. Not only can silver, this is called an interfering ion. Silver will interfere with lead. So as long as we don't have silver there, as long as we separate it out all over here, then we don't have to worry about interfering silver ions because the only thing that should precipitate here is the lead. The barium and manganese won't. Likewise, lead can interfere in this test. So if we don't heat this and make sure all the lead 2 chloride dissolves, then some of the lead makes it over here and we get a white precipitate of lead 2 chloride. And so what tends to happen is people will add sodium hydroxide to that and nothing happens. It doesn't change color. They're expecting the color of the precipitate to change to black. And then they get confused at this point thinking, well, maybe they got a positive for silver ion, but you know, it's not turning black, so it's a very confusing result. And so that could lead to a false positive over here as well. And so that's why we do a confirmatory test. The confirmatory test is adding sodium hydroxide. If we just stopped at a white precipitate, then false positive is very easy to occur because lead, you know, will give a white precipitate as well. And so again, this process is called separation. And the way we separate it is by using a funnel and a piece of filter paper. And so what we do is we filter out this cloudy mixture and capture the white precipitate in the funnel. That's called the precipitate, PPT. And the liquid that passes through the funnel is called the filtrate. And so this is the liquid phase. Now, we have to be careful because the precipitate is going to be wet with solution, and that solution is going to contain lead ions, barium ions, and manganese ions, and that will lead to interferences. So what we need to do is once we get the precipitate in the funnel, we need to wash it. When we wash it, then that means we're going to wash off all the contaminants off of it, that is the filtrate off of it. And in the first rinsing, we want to capture and include, because we don't want to lose that lead, barium, and manganese. So the first rinse will capture and combine with the filtrate. The second rinse and the third rinse, we're going to discard. We're just going to dump those into waste, because the second and third rinse shouldn't have much lead, barium, and manganese. And if we add that, then that could overly dilute these. If we overly dilute these solutions, it makes it harder to detect, because the more dilute the ions are, the more difficult it is to get those to react. And so we want more concentrated, it's better. And so this is the other way we prevent, interferences here, cross-contamination here, is by rinsing our precipitate, or washing. We call it washing the precipitate. All right, so now we got the lead, barium, and manganese, and hopefully no silver over here. And hopefully we didn't lose all the lead over here, because if we lost most of the lead over here, we'll come out negative here, because there's just not enough lead to precipitate. We need a certain minimum amount to be able to see a precipitate, and we might not have it. Now, assuming the separation went nicely, this is what we end up with, and then we need to do another complete separation here. That is, we got to make sure we get rid of all the lead as the precipitate. We got to make sure we get rid of all the lead here, because we don't want lead interfering with subsequent tests for barium and manganese. So if some lead made it out over here, that could lead to interferences over here. So we got to make sure we add plenty of potassium iodide. In fact, we add excess Ki to make sure we got it all out. Sometimes there's a problem with adding too much, sometimes you run into other unwanted reactions that could potentially occur. Okay, once we get this yellow precipitate, we're going to wash it once. We're going to wash it once, not because we need this clean. We're going to wash it once so that we don't lose much barium and manganese, because this precipitate is going to be wet with the filtrate solution. And so we'll give it a quick wash with a little bit of DI water, and then rinse those and combine the rinse with our filtrate. Okay, that way we don't lose ions. We're not washing the precipitate because we're doing subsequent steps. Over here, we're washing the precipitate because if this precipitate is not clean, that's going to lead to ambiguous results in the next step. Here, we're just washing. So we are only going to do one wash of this. We're not going to do 3 washes. This, we're going to do 3 washes. The first wash, we're going to capture as filtrate. The second wash and the third wash are going to be discarded into the waste. Okay, so we do 1 wash, make sure we get the barium and manganese, all of it over here. Okay, then what are we gonna do? Okay, we're gonna separate out the barium next. And so if we treat the filtrate with sodium bisulfate, now bisulfate is just going to precipitate out sulfates. It's not precipitating out bisulfate, it's gonna precipitate out sulfate. So we're gonna lose that hydrogen on bisulfate. Which happens. Even sulfuric acid, if we add sulfuric acid, the same thing will happen. We're going to precipitate out sulfate. It's going to react to completion. And so in this particular case, it's the bisulfate reacts with barium. We lose the H plus, and we're going to get just Ba. So this is what it's going to look like in terms of an equation. The barium ions love sulfate. They don't love bisulfate. But what it's going to do is the barium is going to knock hydrogen off bisulfate. Usually that hydrogen is attached to bisulfate. So barium comes along and wants sulfate. So it knocks the hydrogen off to form BaSO4 solid. And that hydrogen comes off as a proton here, H plus. And so this is just a precipitation reaction. It's metathesis as well. It's just, barium ions like sulfate ions. And that gives us a white precipitate here. Now we have a choice here. This white precipitate is going to be wet with the filtrate. The filtrate is going to contain manganese. So probably the first wash, we'll put the rinsing here. And then we aren't going to do any subsequent washes. It's like a second or third wash because we aren't going to treat this further. And so here, well, here the yellow precipitate means you tested positive for lead ions. The white precipitate here means we test positive for barium ions. Okay, now sulfate and manganese don't react. You know, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So barium is one of those exceptions. Manganese sulfate is soluble, and so manganese makes it through here. In this case, what we're going to do with the manganese here is we're going to precipitate it out with hydroxide. Manganese and hydroxide like each other here. And so let's do that. Here. So we'll have manganese and the 2 hydroxides produces a brown precipitate of manganese 2 hydroxide solid. And so the first positive indication that we have manganese is this light brown precipitate. Now this light brown precipitate we're going to wash. The first wash we'll discard, the second wash we'll discard, third wash we'll discard so that we have clean manganese 2 hydroxide precipitate. We aren't going to do anything with the filtrate. It's just going to go into waste. Okay, once we have the clean light brown manganese 2 hydroxide solid, then we're going to treat it with some nitric acid and something called sodium bismutate. Sodium bismutate is an even stronger oxidizer than nitric acid. And so H plus and bismutate is a powerful oxidizer. Stronger than permanganate. We'd have to know what the bismutate goes to, you know, to get the balanced chemical equation. And so what we're going to do is we're going to convert manganese 2 hydroxide into permanganate. And so the reaction is going to be this skeleton. Manganese 2 hydroxide gets oxidized to permanganate. Okay, and then the bismutate gets reduced to, I don't know, we can kind of think about different products for bismutate that could go here, but the best thing is to analyze it. And so let's see if we have that particular reaction in the discussion for this particular step. This is a very interesting redox. Bismutate is a very expensive oxidizer. So I'm going to go back to the discussion section and then take a look. Yeah. So it looks like the bismutate gets converted to bismuth 3. And this is sodium bismutate solid. I should have left it as solid. And so we'll have to go, excuse me. It's solid, but all sodium salts are soluble. And so even though it's a solid, eventually it will dissolve once it hits the water. So the bismutate goes to bismuth 3. And so that came from analysis of this. And then we could just balance these 2 half reactions. So for example, if we balance this one, we have 1 manganese on the left, we have 1 manganese on the right. So the manganeses are balanced. Check. Then we balance the oxygens. We have 2 oxygens on the left, we have 4 oxygens on the right. So we need to add 2 waters to the left, so plus 2 H2Os. And then we balance out the hydrogens. So we have 2 hydrogens from here and 4 hydrogens from here. So we have 6 hydrogens on the left. We have no hydrogens on the right. And so we need to add 6H plus to the right. And then we look at the charge. Manganese 2 hydroxide is neutral, water is neutral. So we have 0 charge on the left. And then we have -1 plus 6 is going to give us +5 on the right. And so we balance the charge by adding negative charges, electrons. So we'll need 5 electrons to get it to equal. And so the half reaction here, let me just write it up here. The half reaction is going to be MnOH2 plus 2H2O. This is an insoluble solid, 2H2O, yields permanganate plus 6H plus 5 electrons. Then we just check atoms are balanced, 1 manganese, 2, 6 hydrogens, 2 plus 2 is 4 oxygens, and then 0 charge, -1, -6 plus 6 is 0 charge. So this is balanced here. The other half reactions, bismutate goes to bismuth 3 ion. And so bismutate goes to bismuth 3. So we have 1 bismuth on the left, we have 1 bismuth on the right. So the bismuth are balanced. And then we have 3 oxygens on the left, we have no oxygens on the right. And so we'll need to add 3 waters here. And then we'll have 0 hydrogens on the left, and we'll have 6 hydrogens on the right. And so we'll need to add 6H pluses to the left. And then let's look at the charge. -1 plus 6 is +5, +3, and 0 is +3. So we have a +5 on the left, +3 on the right. And so to get these to balance, I'm going to have to add 2 negatives to the left, plus 2 electrons. And so the other half reaction is bismutate, BiO3 minus, plus 6H plus 2 electrons, yields bismuth 3 plus 3H2O liquids. All right, and so we need to add these together. So I'm going to multiply the top one by 2. That's going to give me 10 electrons here. And then the bottom one by 5. That'll give me 10 electrons there. And so combining these two, I'm going to get 2 permanganates, or not permanganates, manganese 2 hydroxides. 2 manganese 2 hydroxides is a solid plus 4 H2O plus 5 bismutate plus 30 H plus 10 electrons yields 2 permanganates plus 12 H plus 10 electrons plus 5 bismutate plus 30 H plus 10 electron. Oops, am I doing this? Sorry, I need to go products here. I made a mistake. It's going on the reactants. I have 2 permanganates. Okay, so I'm here, 10 electrons. This is going to be plus 5 bismuth 3. Plus 5 bismuth 3 plus 15 waters. So next step is we're going to look what we can cancel out here. And so I have 4 waters on the left. I have 15 waters on the right. So I'm going to change this to 11 waters. I have 30 H plus on the left. I have 12 H plus on the right. So let's get rid of those 12, and that's going to make this 18 H plus here. I got 10 electrons on the left. I got 10 electrons on the right. These need to cancel. And so overall, the reaction is going to be this. Two Mn manganese 2 hydroxide solids plus 5 bismutate plus 18H plus yields 2 permanganates plus 5 bismuth 3 plus 11 H2Os. 11. Liquids. These are all aqueous. I didn't write aqueous though on the non-aqueous. I just write solid, liquid, gas, and the rest are aqueous. There's a driving force for this reaction here. There's a driving force because they're telling us this reaction occurs. We really wouldn't be able to predict it because we need to know, you know, this is our oxidizer here. This is our reducer here. Going backwards, this is going to be our oxidizer here. This is our reducer. So, you know, how does permanganate compare to bismutate? Well, it turns out this is stronger. This is weaker, even though permanganate's a top 5 on our chart, you know, top 5 oxidizer on our chart, it's weaker. Bismutate is pretty strong oxidizer. Now, they're using sodium bismutate, so I need to add, you know, if I wanted to do that, I got to change bismutate to sodium bismutate. And so they did this. I could have put it in there. I'll have to add 5 sodium. And so I'm going to take this out of solution and make this back into the solid. Sodium salts are all soluble, 18H plus. And so the difference is if I switch that, I need to add 5 sodium ions on the right. And so 5 sodium ions plus everything else is the same on the right. So basically this is what's going to happen here. So we're going to form the purple solution. Permanganate has a characteristic grape juice color to it. And so what's going to happen is we're going to get some purple solution form from this. If we get a purple solution indicating permanganate, then this is a positive test for manganese 2. Looking for that purple solution there. Okay, so what I need to, any questions on this? We went through the whole analysis basically, and then we'll just go ahead and do it, run it. And so I need to set it up. So let's take another break. Let's take a 15-minute break now so I can get everything set up. Actually, let's take a 20-minute break. I need to clean up this stuff here with the titrations. And so what I decided to do is to save time, and plus I had to do 8 trials. I had to do 8 trials of day 1. And so it took longer than expected. And so we're going to skip day 2. Day 2 is essentially the same thing, except we're just analyzing a different acid. That's all. And we don't know what the concentration is, so we're standardizing an acid. Day 1, we standardize the sodium hydroxide. Once the sodium hydroxide is standardized, then we know the concentration. We just took the average, which is 0.1021 molar. And then we can use that for analyzing unknown acid solutions, which is acetic acid. And so But I think you got the gist of the titration. I tried to make it as realistic as possible. You know, if things work out too perfectly, then it's not realistic. You know, in lab, everything that can go wrong will go wrong. So, you know, in lab, you have to have some degree of persistence. So, well, anyway, let's stop. We're going to take about a 20-minute break. I'm going to clean up my titration stuff and then set up the unknown analysis, the qualitative analysis, known and unknown. Okay, so we'll be back. I'm going to pause it here. No, no wonder.
On mute.
Okay, can you hear me?
Yeah.
Okay, thanks. What I was saying is that since I'm skipping part 2 of the titration, I'm going to add just one more calculation to ours. Day 1. I know what the molarity of the sodium hydroxide is according to the stockroom. And so we'll just do the actual molarity. This is based on the stockroom. Now the solution has been sitting, I don't know for how long, and sodium hydroxide is one of those things that reacts with CO2 in the air. CO2 is an acid. And so when sodium hydroxide reacts with CO2, that's why when you store sodium hydroxide, you got to watch out. Not only will sodium hydroxide react with CO2, but sodium hydroxide also reacts with glass. Take a look at, this used to be clear glass, but now this glass is heavily etched because the strong bases will etch glass. And so normally when you buy sodium hydroxide, it comes in plastic, not glass bottles. It depends on the concentration. You know, this is 6 molar, but if we have lower concentrations, glass doesn't look as bad. This is 1 molar sodium hydroxide here. And so I'm not sure if this is still accurate, but we'll just take it as accurate. And so this is our theoretical value here. And so the percent error is the experimental value. From this experiment, we calculate an average molarity of 1021 molar. So that's experimental based on the titrations minus the theoretical, which is what it should be according to the stockroom. This is theoretical. Divided by the theoretical times 100%. And so what does that come out to? So I'm just going to go ahead and do 3 divided by 1024 times 100. 0.29. 0.29% or 0.3% error. So that's what we got for our titration, a 0.3% error. All right, and then again, we're skipping part 2, skip day 2. In fact, day one took me 2 days or more. I don't know how many days it took. I was looking, I couldn't find the known solution. I don't know where they keep it, and it wasn't with anything else. So what we're gonna do is we're gonna do experiment 12, day 2. I'm gonna skip day 1. Day 1, we're running known solutions. Day 2, we're running unknown solutions. So we're just going to run unknown solutions and see what they give us. You know, we'll just analyze a bunch of unknowns. I have a bunch of unknowns. I could find those. I couldn't find the known solution though. And so the only thing, this flow chart, you know, we could use this flow chart. I don't really need the procedure. The only thing I need from the procedure are the concentrations. They didn't write the concentrations here. You know, so what concentration of sodium hydroxide should I use? Actually, in this case, it doesn't matter. In the silver nitrate and the barium nitrate, these aren't so critical, the concentration, because I know the reaction, you know, what's supposed to happen in the reaction. So it won't be difficult to figure. So I got some test tubes here. And we got to label the test tubes. So I got my Sharpie here for labeling the test tubes. Okay, for the first one, for the ammonium, I want to do it in a small beaker. That'll be easier. Oh, what's the smallest beaker I have? My small beaker is dirty, so I'm going to use a 150 milliliter beaker for this. Okay, so I'm going to test some unknowns for, actually I need to get a waste beaker here. Get a waste. So I'll get a beaker. I'm going to label it waste here. And this is going to be experiment. And since the numbers are all screwed up, I'm just going to call it qual, experiment qual for qualitative analysis. That way I don't need to know the numbers. All right, so the first experiment we're going to do is we're going to test for ammonium ions. So I'm going to get an unknown here. And I'm supposed to get 3 milliliters, but you know, I'm not going to measure it using a grad cylinder. What I'm going to do is I'm going to just use this pipette here. This is what we call a plastic pipette or plastic dropper. And this one, let's see if I have better ones than this. No, I just got this. This one, usually about 1 squeeze of the bulb is about 1 milliliter. And so I'm just going to do 3 squeezes, and that should be about 3 milliliters of unknown solution. And so here's our unknown solution here. And so I'll do 1. Okay, normally, you know, you don't put pipettes in this, but this pipette is clean. Brand new, and this pipette's only going to be used for this unknown solution, so I'm not contaminating the unknown. And so that's three squirts. Okay, this is, I'm going to write unknown A here, so I keep it separate. And then to keep this pipette clean, I'm going to put it in the test tube. Somebody put labeling tape on this, so I'll just write on the labeling tape. You don't need a Sharpie to write on the labeling tape this. And so I'm just keeping the pipette clean here. That's for unknown A. And I'll just use it for unknown A. Because we're going to test unknown A, I need more sample of unknown A as well. Okay, then what I'm going to do is I'm going to add sodium hydroxide. Here, 6 molar, 1 molar. Doesn't make much difference. I just have to, I can use less of the 6 molar. I have to worry, you know, if it gets too concentrated, there's potential for violent reaction. Violent is not redox. This is just acid-base. So violent acid-base just generates a lot of heat, steam. Okay, now I got to get this to stick on the underside of the watch glass, but it's not going to stick on the underside of watch glass unless I wet it. And so what I'll do is I'll get the squirt bottle and then I'm going to wet this. So now it'll stick. So if I flip this upside down, it's not going to fall off. There. And so it's stuck on the bottom of the watch glass. I'm going to use the watch glass as a cover for this. So if I cover this right now, there's no gas being generated. And so you know, it stays red. This is red litmus here. Okay, so what I'm going to do is I'm going to add some sodium hydroxide to this. The sodium hydroxide is going to react with ammonium to create ammonia, and that should generate ammonia gas. It also, if you look down here, it also created a precipitate. And so you can see a precipitate there. So we get some clues. What color is that precipitate? Well, it's kind of a white, brown, light brown. And so if you look at the interfering species here, you know, we got dark brown precipitate, which is silver oxide. Maybe that's some dark brown precipitate. Maybe there's some white precipitate mixed in there, which is lead 2 hydroxide. And maybe there's some light brown precipitate mixed in there, which is manganese 2 hydroxide. But you guys need to make sure I'm sharing that screen. Oh, no, I'm not sharing it. Oh, maybe I am. And so what I'm looking at is down here. Okay, let's see if anything's happening to the litmus. No, it doesn't look like anything's happening to litmus. So what I'm going to do is I'm going to just stir this up a little bit. Sometimes a little bit of heat helps to drive off the ammonia. And so I'm going to gently heat this a little bit because these are little tricks you can do once you you're more familiar with. I'm not going to use much heat, and it shouldn't take much heat to. Oops. So I have a very, very small flame on there. And then I don't want to burn my fingers, obviously. It could. This is very dangerous. Like this. All right, that's probably enough heat. And so I just needed just a little bit of heat to make sure. And then we look. Do you see any blue color in the litmus? Anybody? No. All right, so what does that mean? Okay, no means negative for ammonium. And so this is unknown A. We have negative for ammonium. A negative for ammonium means maybe we have ammonium, it's just too little to detect. But that's what we have so far. Let me do one more ammonium test on a different sample here. Actually, I have no idea what these are. I'd like to get something with ammonium. Actually, let me give you something with ammonium. Ammonium is apparently it's missing from the kit here. I didn't realize it's missing. I'll have to do ammonium. I'll do it a little bit later. I'll have to dig around for some ammonium. Unless I have some. This other card. Let me check this other card. I'll have to dig around for the ammonium. I don't know where it went, but it was supposed to be on the card. So, okay, after we do the ammonium test, let's go ahead and do the chloride test next. And so I'm going to use unknown A. And we're going to test it for chloride this time. So I need about 3 milliliters, it says, for the mixture. Actually, I really don't need 3 milliliters. I think I can get by with 1 milliliter. I'm just going to do 1 squirt of this in the test tube. This test is really sensitive. And so that's about a milliliter there, 1 squirt. Oops, this was the wrong one. I'll have to make a little more of these. Okay, and then I'm going to add some silver nitrate to this test tube, and let's see what happens. Now, this is the COVID-19 edition of this. In your chem lab, you aren't going to have you're going to have a transfer beaker. And so it should be poured into the transfer beaker here, but I'm trying to minimize waste, and I'm using clean pipettes, brand new clean pipettes. And so this is normally what you don't do. You don't normally put a pipette in the original bottle, but I am. Here. Okay, so I have my silver nitrate in the pipette, and then I'm going to slowly add it drop by drop, and let's watch what happens to see if we get any precipitate. So here goes. So I added about a mil. So I had about a mil of unknown, and I added a mil of silver nitrate. Now silver nitrate, I don't want to spill this on my fingers, obviously because it's stained them black, but I have these gloves on anyway. Okay, did you see any precipitate? Okay, no precipitate here. So no precipitate here means negative for chloride. So far we have 2 negative tests. So we have negative for ammonium and negative for chloride. This is unknown A. Okay, the next thing we're going to test for is nitrate, the brown ring test. And so this is waste here as well as this. You know, this is the waste. Let's check our ammonium. There's still no evidence of blue, so I'm sure ammonium, nothing happened there. So I'm going to dump this in the waste container, which I have set down here. And the same thing for the ammonium test. I'm going to just dump it into the same waste container here. And then let me cleaning. Okay, this is a dirty test tube. So I'm going to put that over here. Okay, so now I need a fresh sample of unknown. So I'm going to get another squirt of unknown here. And this is about 3 milliliters, they say. So in this case, you know, I'm going to use about 3 squirts of my unknown here. We'll go with 1, 2. This doesn't have to be so accurately measured. I mean, these are unknowns, and then we'll adjust it. We'll adjust it based on what we see, you know, the reaction happening. And so I got my 3 squirts of unknown here. And now we're going to test the unknown for the presence of nitrate. So I need some iron 2 sulfate. I have my iron 2 sulfate here. Okay, so I'm going to add about the same amount of iron 2 sulfate. In fact, I should have just done 2 squirts. You know, 3 squirts is too much, I think. And so I'm going to pour iron 2 sulfate almost to the bottom of the tape here. Now I'm using a medicine dropper here, and the medicine dropper is not going to be 1 milliliter per squirt. Look at that. You see that? I have a precipitate in there. And so something loves sulfate. Something is precipitating out with the sulfate in iron 2 sulfate. That could make it difficult to see the brown ring, this precipitate. And so that precipitate could be lead 2 sulfate, or it could be barium sulfate, or it could be both. And maybe there's a light brown or dark brown. Dark brown, I don't think there's dark brown in there, but it could be. This could be very dilute. Okay. Now I need to add my concentrated sulfuric acid. This is going to be in this jug here. Let me set this down here. The concentrated sulfuric acid is 96% sulfuric acid, 96% by mass. 96% by mass means we have 18 moles of sulfuric acid per liter. And so this is really concentrated. This is what turned the sugar into charcoal. Okay, I don't know what that is on the bottom. There's some stuff on the bottom of this. Put that there. All right, to prevent accidents from occurring, what we have here is an auto dispenser or an auto pipette. In the auto pipette, we can set, to how much we want to dispense. So right now it's set to 0 milliliters. So I'm going to unlock it. There's a lock here. So this is locked. This is unlocked. No, actually, this is unlocked. And so I'm going to unlock it, and then I'm going to set it to 2 milliliters. I want about 2 milliliters of concentrated sulfuric acid, and then I'll set it. I have a little less, but it doesn't matter. The amounts need not be exact. Now, when we add acids, it gets very hot. So I don't want to hold the test tube with my fingers. I'm going to use this to hold the test tube. And let's see, let me adjust and so I'm going to use a test tube clamp to hold my test tube so I don't burn it. I still have a bunch of precipitate in there, but the precipitate's starting to settle on the bottom. That precipitate is going to make it hard to see the brown ring. So I have two choices. I could filter it. If I filter it, then maybe I'll be able to see the brown ring easier. But to save time, I'm going to try to not filter it and get the sulfuric acid to sink to the bottom, and then look for the layer, the interface between, because the sulfuric acid is going to take time to mix with the water. And so I'm going to pour it slowly down the side. So it runs down the side into the bottom. And I'm not going to grip it with my fingers, otherwise they're going to get very hot. And so to work an auto dispenser, this is what you'll do. You're going to, this is a syringe, basically. And so you're going to hold the test tube here at an angle of about 45 degrees, like this. And then you're going to rotate this back and forth until you pull the syringe plunger all the way up until it stops. And now it will dispense 2 milliliters. So what I'm going to do is I'm just going to gently push the plunger in, and then slowly, drop by drop, let the sulfuric acid drip into the solution along the bottom wall of the test tube, like so. Okay. Now take a look at what happened here. You see the sulfuric acid is this CCS, the clear colorless solution at the bottom, and it's very hot. Yeah, it's very hot. And so it's there at the bottom, and it's kind of pushed the precipitate up. And so I'm going to look for the development of a brown ring somewhere in here. That precipitate could be messing it up here because the precipitate is acting like a plug here and not letting reaction occur. But definitely the sulfuric acid sunk to the bottom. So this one looks negative, but I'm thinking maybe it's a false negative because of this plug of precipitate that's stuck here. And I probably should have filtered it. And so I'm going to repeat this one, and this time I'm going to filter it. I'll let this one sit aside here for a minute and see. We'll come back to it and see if the brown ring forms or not. I'll let it sit aside. Let's go to the sulfate test. And so I'll need another 3 milliliters of my unknown. And you know, we're going to test for sulfate. Let's see if our unknown has sulfate in it. And so, you know, 3 milliliters is too much, I think. I only need about 1 ml. And it's not that hard to see a precipitate. And so I'm just going to do 1 squirt here. 3 squirts seems overkill. Okay, so I have my unknown here, and then I'm going to add barium nitrate to see if I get a precipitate. So I'll add about a squirt or 2 barium nitrate. Let's see if 1 squirt will do it. And so I got my barium nitrate. Let's keep an eye on the bottom of the test tube. All right, that was a full squirt. Maybe let's mix it. I'm going to mix it by tapping it like this. And it doesn't look like I have any precipitate. And so let me add 1 more squirt of barium nitrate to see. You know, maybe it wasn't enough. Okay, and then tap it again. There's no precipitate there. There's no precipitate. I'm going to dump that. Okay. So, where does that leave us? That leaves us with 3 negatives. But we have to have an ion in there. And so I'm still thinking that this one didn't work successfully. And so I'm going to redo this one. So I'm going to dump this. Dump this into the sink. I'm going to clean that test tube. Okay, and then I'm going to repeat that reaction. But in this case, I'm only going to do 1 squirt of unknown. Actually, maybe 2 squirts because I'm going to filter it. So I'll do 2 squirts of unknown. 1, 2. 2 squirts of unknown. And then I'm going to add about the same amount of iron 2 sulfate. Let me see if I got a better, fresher solution. Let's try this one. One. Okay, again, I get that precipitate. Here. 2. Okay, 2 squirts of the iron 2 sulfate. Okay, now I'm going to filter it. And so how am I going to filter it? Okay. You have a funnel. This is just a plastic funnel, and you might have a glass funnel. Glass funnels are fine. They're just easier to break. And then we support the funnel. We're going to support the funnel with something called a clay triangle, like this. The funnel can sit in the middle of the clay triangle. And then we have a ring. And so the clay triangle can sit on a ring like this. And then we'll put it on a stand, a ring stand. A ring stand here. Like this. And then what we're going to do is we're going to filter out that precipitate. Out of the test tube. So I have filtered, they have different types of filter paper. This is number 413, qualitative. And it depends on what pore size you want in the filter paper. It depends on how much you want to catch. Now the filter paper is a round circle like this. And we got a conical cone-shaped funnel. So we have to fold the filter paper. When you fold the filter paper, you fold it in half once, like this. And then you fold it into a quarter section like this. Now I was taught to tear off an edge, but I don't bother doing it. I can never see the edge, and it didn't really improve filtration. Okay, but the filter paper doesn't stick, so we got to make it adhere to the funnel. So what you're going to do is you're going to separate it, but you're going to end up with 3 sheets of filter paper on one side and 1 sheet on the other side. It's no big deal. And then we're going to wet the filter paper to make it adhere, just like we did to the litmus paper. Let's wet it, make it adhere. And then let me get rid of the excess water by dumping it into the waste. So now I just got a damp piece of filter paper there, no excess water. I'll throw it down like this. And so what I'm going to do is I'm going to use a test tube here like this, and I'm going to filter the precipitate, and then the filtrate, the liquid should go down here, and then I'm going to test the liquid for nitrate. And so what I'm going to do is I'm going to stir up this. Sometimes you don't want to stir it up because it'll clog the filter paper, but I'm just stirring it up to make it easier to pour. And then I'm just going to dump it into the filter paper here, like that. And so this is dirty, so you can put that into the wash beaker over here. Okay, with more quantitative filter paper, it just filters a lot slower, but it captures more. So the tiny particles of precipitate actually make it through here, but they're hard to see, and they shouldn't interfere with much. And so we should be okay. All right, this is slowing down. So since it's slowing down, I'm going to do this. I'm just gonna, I don't need to capture every drop of it. I have plenty here to test. That should be plenty to test. All right, now let me do the concentrated sulfuric acid. Let's see what happens here. So I got my auto dispense. I'm gonna hold the test tube with the clamps because sulfuric acid create a lot of heat, and then let's test it out. So lift, twist back and forth to lift this up until it stops at 2 mils, and then just slowly depress it. I rotate it so I can get a nice drop rate. I don't want to mix it too fast because I want this sulfuric acid to sink to the bottom like syrup. I don't want it really to mix with the water because I want that brown ring. Okay, now let's take a look. Do you see it? Look at the interface between the sulfuric acid and the green solution, or it's above. And at that interface, there's a layer. Do you see the brown layer? Okay, this is the famous brown ring. And we couldn't see it before because that precipitate was interfering with the interface and not letting it react. It's going to react at where the H plus from the sulfuric acid combines with the nitrate to, and there's not much nitrate and to oxidize the iron 2. The iron 2 is still in there. The iron 2 is the green. You can see a slight green color to the upper layer. Okay, so at least we tested positive. Now we finally got a positive test. This unknown A is positive for nitrate. We have nitrate ion. And so we'll just mark that in our notebook, positive for nitrate. And then what I'm going to do is I'm going to dump this into the waste. I got to be careful. It's concentrated nitric, but you know, we got the nice brown ring. That's actually kind of purple. You know, this is a Lewis acid-base reaction. NO, it's like oxygen. Oxygen, when it reacts with your hemoglobin or sticks to it, it's a Lewis acid base. Lewis acid is iron 2, the same here. And the Lewis base would be, in this case, NO, or the Lewis base in your body would be O2. O2 you wouldn't think of as a base, really. This test tube is extremely hot. You wouldn't think of it as a base. It's extremely hot because this concentrated sulfuric. Okay. And so here we had to do an extra step, but sometimes, you know, this is why you want to know what's happening, because sometimes you have to do modifications on the fly. You know, it's hard to write instructions for every possible scenario that comes up. And so the instructions are just kind of a general guide, but the more you know about the underlying, you know, reactions and theory of everything, you know, the more you can make little adjustments to make your reactions go a lot smoother. Let me fill this up with some more soap water, since I'm going to run out of test tubes. We have to wash some. Okay, now we're done with this. These are the individual tests. Now we're going to do that series of tests, the flow chart. Now, when we do the flow chart's missing some things, the concentration. I want to know what concentration of HCl they're asking for here. And so let me, that's something we should put in the flow chart, because I'm not using the procedure at all. I'm just going to use the flow chart. The reason I'm going to use the flow chart is because it's faster that way, and I know what the reaction should be, and so I know what to look for. I just want to make sure what the concentrations are. So I'm going to go up. Actually, I don't know if you can see what, I know you guys, I'm sharing this, but I wonder if you could resize the other window. Six molar HCl. All right, so we're just going to use a more concentrated HCl. 6 molar. Let me grab it. I should still have some earlier. Now, this HCl, when I went to grab it, I noticed that the lid, you know, on this was loose. If the lid's loose, then this is going to go flat. You know, the HCl is just going to evaporate off. So hopefully this is still good. We'll find out. Now, they're saying that we want 12 milliliters to start. You guys, actually, maybe just leave it on the flow chart here. I'm trying to show 2 screens. I don't know why they put the amount there. They should have put the concentrations, and then we wouldn't need the procedure at all, because, you know, as long as we know what we want to do with the reactions, we're okay. And so we want about 12 milliliters, which is going to be about 12 squirts, which is a lot. But let's start off. I'm going to do 3, or maybe I'll do 4. 1, 2, 3, 4. So I put in 4 squirts of unknown in there. Okay, so if I do 4 times 3, then that's 12 milliliters. And it does, like I said, it doesn't have to be exact because we can always adjust the amounts on the fly. So I'm going to fill this up. If that's 1/3, I'll fill it up to about here where my thumb is. And so I'm just going to pour it here. Okay, so that's about 12 milliliters or close enough to 12. Okay, now I'm going to add the HCl. Now, how much HCl do I need to add? I'm not even going to look. How much HCl I need to add is I got to make sure I precipitate out all the silver. All the silver needs to precipitate. And so how am I going to get all the silver out of there? Well, I'll just keep adding until I see no more white precipitate form. And so I got a lot of white precipitate there. So I'm going to keep adding until I see no more white precipitate form. But here, it's kind of hard to see because it's so cloudy that if I add another drop, I can't see anything happen. And so what I have to do is I have to wait and let the precipitate settle a little bit and then check it. But there's another way or another thing I can do as well. And the other thing I can do is, and I have to do this anyway, is heat it. Heating it helps coagulate the crystals so that they grow bigger and sink faster. And so I'm just going to go ahead and start heating this. Now, it's kind of dangerous heating because, you know, the flame is extremely hot, right? And the danger is overheating it. And so one way to prevent overheating is, okay, so I'm going to switch out. I had the triangle, clay triangle. I'm going to switch that out for wire gauze. So I'm going to put a wire gauze on the ring here like this. And then I should have done this earlier because it takes time to heat up water. I'm going to make what's called a hot water bath like this. And I'm going to get one big ring because in case, you know, I don't want the hot water bath to fall over and spill everywhere. Hot water can also cause 2nd degree and 3rd degree burn. So I'll have it set up like this so the beaker can't get knocked over. And then I'm going to try to get some warm water here. Just warm water. Now, you know boiling water takes time. So this is something you should, you know, pre-plan. And so what I did was something called pour planning. If I had read through this experiment completely, I would have known that I needed a hot water bath. And I would have set that up first thing before I started any work, before I went to the stock room, before I did anything. I would have set up my hot water bath, which consists of about a half full beaker here. A half full beaker, and then we're going to put the test tube in there to heat it up. This way, you know, it can't exceed 100 degrees C, you know, or roughly there. It depends on how pure the water is. But the water's max temperature is going to be about 100. The flame is, you know, 600 or maybe even closer to 900, depending. I don't think it's that hot, but the book says. And so I'm going to get the flame going here. And then start my hot water bath. Try to get as big of a flame as possible with a cone. Okay, that looks okay. And then let me rotate this the flame on there. Okay, watch out, never touch hot, you know, never touch metal because it could be very hot. We don't know. Hot metal and cold metal look the same, so burns are quite common. Now this burner is too low, and so I'm going to raise up the burner height here. I can raise it up with my hand, you know, to heat it that way. But I'm going to use a clay and to try to raise it up a little bit. Still a little bit too low. And so let me grab a couple of more. When you get to organic chemistry lab, we don't have to use things like this. We get fancy little things called lab jacks. And lab jacks is you put a lab jack in there and then it's like a little elevator platform. You twist a knob and you can raise things up or lower things down. And so it makes adjusting the height of things a lot easier by using a lab jack, you know. But we don't have a lab jack, so I'm just gonna heat this like this. Now I could put some boiling chips in there as well, you know, to promote smooth boiling. So let me grab some boiling chips and then we'll be all set for this. Boiling chips are just little quartz crystals. Dump some boiling chips in there. Okay, while that's heating, you know, don't want to waste the time. And so what we can do is we can test some other, I'll leave the, I'm going to heat this up in here. I'll just leave that in there. We'll test some other unknowns and see what we get. And so that was unknown A. We're going to test it. Unknown B. Did I already test unknown B? Which one did I test? No, I just tested unknown A. And so let's go ahead and test unknown B. I want to test unknown B for ammonium first. And so while this is heating up, let's try a different unknown. And so we're going to test for ammonium. I need that small beaker. I don't really have a small beaker anymore, so I'm going to use a 250. Just make do with what we got. And so I need to label the test tube B here for unknown B. This one I don't have any labeling tape, but I'm just going to write on here B. Okay. And then I'm going to have a pipette for B here. And so this I'm just going to use to transfer. So for the ammonium test, I'm going to use 3 squirts because, you know, it's not that sensitive. We're testing for the gas. So is this it? Do 1. 2. 3. So that's 3 squirts, about 3 milliliters. No B. Okay, then I need to set up the, you know, we need a way to capture the gas and test the gas that's coming off this. And so I got my watch glass. There's some stuff on this one. It wasn't cleaned so well. And I have my red litmus. Bases turn litmus blue. Bases are blue. Acids turn litmus red. And so red should turn blue. Blue should stay blue. So again, it doesn't stick to the bottom. And so I'm going to wet it. And so I have my wet piece of litmus there. The waste here. Clean. Okay, so now I'm set up for testing the gas. Any gas that's generated here is going to rise up and hit the litmus. And so I'm going to dump in some sodium hydroxide in there. Now, how much? Plenty. You just need plenty of sodium hydroxide in there. And this sodium hydroxide is 1 molar. I think I had some 6 molar sodium hydroxide, a bit more concentrated. So let me find that 6 molar sodium hydroxide. maybe not. I don't see it. Oh, there it is. Okay, so here's my 6 molar with the etched glass. And how much do we want? We want lots. We want to make sure there's plenty enough to react with all of it. And so I'm going to take my beaker here. I removed the lid, and I'm just going to pour in my sodium hydroxide. This little medicine dropper is so slow. And so I have plenty. I have more sodium hydroxide than unknown in there, it looks like. And then I'm going to cover it. I got a white precipitate for unknown B too. You can see there's a white precipitate down there. And then I'm going to gently mix it like this. I don't want any solution to splash up and hit my litmus. I want the gas to slowly rise up and then to turn it blue. Also, heating it helps a little bit. You know, if there's gas, we can heat it a little bit. So I'm just going to warm it up just gently here. Let's see if we see any evidence of blue. Actually, no, I don't see any evidence of blue. Try warming it up a little more. Wow, this is kind of interesting. What happened to my white precipitate? Take a look. The white precipitate appears to be dissolved. I still don't see any blue. I would see a gradual change in blue. So I'm going to set this aside in case it's a slow reaction. Now this is bumping a little bit. Did you hear that noise? This test tube can be hot too, so I can use a test tube clamp to hold it as well. So we'll just keep heating that. So that was unknown B, and it looks like it's negative. It's negative for ammonium. Here, still not blue. I want to do one that's positive for ammonium, so hopefully the next unknown will have a positive test for ammonium. Okay, then we're going to test this for chloride. And so for chloride, I just need 1 squirt. I don't need much. And so I have a clean test tube, then 1 squirt of unknown B. And then for chloride tests, we're going to add some silver nitrate. Silver nitrate I have over here. Okay, so here goes silver nitrate. Looks like nothing happened with the silver nitrate. So it looks like it's negative for chloride. Negative for chloride. Dump this in the waste. Okay, and then we're going to test it for nitrate. Okay, now you can see my boiling water bath is a nice boil. The boiling chips are working well. They're making nice little bubbles there. So I'm just going to let that go. Okay, let's see. Next is going to be sometimes we have to do careful measurements, you know. But for qualitative analysis, we just got to make sure we have enough to react completely. So I'll probably just do 2 squirts, about 2 milliliters. And then right there. And then I'll add about the same amount of iron 2 sulfate. This will be about 2 squirts of iron 2 sulfate. Let's see what happens if we get a precipitate here or not. And we do a precipitate there. One. When I use these pipettes, I got to make sure I don't contaminate things. That is, I don't want to touch the tip of the pipette to the glass because that could lead to cross-contamination. I don't want cross-contamination to occur. Here. I got a lot of precipitate. I got this much precipitate. I need to filter this out probably. Otherwise it's going to be, although this precipitate doesn't look as dense as that last precipitate. So it might work. Might work. Let's take a look at what's happening here. Now, what's happening here, ooh, this is hot. You know, you got to watch out. These test tube clamps can get hot too. Depends on how it heats this first. And so what I'm going to do is I'm going to use a paper towel to hold on to it. Pretty hot. What's happening here is you can see the precipitate's coagulating on the bottom. You know, I mean, it's coagulating, so it's growing into bigger crystals, and those crystals are sinking to the bottom. I don't want to stir this because I want it to settle to make sure I precipitated out all the silver. Remember, if silver sneaks through, then that leads to interference. And so I'm going to just let this heat longer to coagulate more. Well, that's heating. What I'm going to do is I'm going to filter this probably. Yeah, let's go ahead and filter that. And so that means I need to clean my filter. Not filter, I don't need to clean the filter, but I need to clean the funnel. Now I have some filter paper in here, and it's got some precipitate in there. And I need to put that into the waste. So I'm going to have a solid waste and a liquid waste. And so the solid waste, what am I going to do with the solid waste? I need another beaker. I ran out of beakers. I'll grab another beaker. Okay, so I have this. Normally you don't want to handle these with your fingers, you know, because there could be stuff on there. So you get a spatula and you scrape the filter paper out with a spatula. Sometimes we need to keep the precipitate. Sometimes we can throw it away. In this case, we'll just throw it away, but we'll try to look. It looks like there's a white kind of silver, kind of gray precipitate in there. Okay, and then I got to clean this funnel. But I'm not going to do the full cleaning regimen because I don't have enough time. And so I'm just going to rinse this with some DI water. Like this. It depends. If you need to get it really clean, then you should use soap and water. Probably I should use soap and water. And then fully clean it that way. But I know, actually I know these tests here. We have little pipe cleaners to clean the stem of the funnel, but I don't think we have any here in the lab. No, we don't. So I just gave it a rinsing. I'm gonna get a fresh piece. I know this test isn't super sensitive. If this test were super sensitive, then I'd be cleaning this a lot. Like for example, sodium, I'd be cleaning it a lot. But you know, nitrate, we need quite a bit of nitrate to test positive for this. So it's not the most sensitive test. So if we just have a trace amount, we aren't gonna get much of a brown ring forming. And so I'll get the filter paper to adhere, dump out the excess water, you know, here. And then let's go ahead and filter this. This is the precipitate. The precipitate looks a lot less creamy. This one looks more like it's settled on the bottom there. Now I'm using the ring stand for that, so I'm gonna just do this holding it in my hand like this. And I'll just filter. I'm gonna just dump this in here. I'll leave most of the precipitate in the test tube. here. I just need the solution here. And so if I dump in the rest of this precipitate, it'll clog filter paper. I'm just going to dump this to waste. It's still kind of slow. This is drip, drip, drip. You can see there's still quite a bit of solution up there. Maybe the angle's not so great. Okay, this isn't finished filtering, but that's enough solution to test. I just need enough to test. And so I'm going to stop it halfway. It's probably filtered it about halfway. Okay, now I have the iron 2, and I could add more iron 2 to this because I already precipitated it out, I think. I think I pretty much precipitated it out. Let's see if I get more precipitate. No. I pretty much precipitated out all the stuff. And so I had more iron 2 sulfate. I didn't get any more precipitate. You see that? But I need a lot of iron 2. It makes the test a little bit more sensitive. Okay, then I need my sulfuric acid. Let me grab my sulfuric acid. Here. Okay, and then again, I'm going to twist this back and forth and raise it until it stops. Okay, and then just slowly twist it back and forth and depress it and let the drops go down the bottom wall. Test tube. Hit. Well, this is not exciting. Take a look. Do you guys see that? What do you see? What do you call that? What do you call that? Anybody? It's not a precipitate. It's a liquid layer. It's actually a liquid, aqueous. It's just because there's heavy syrup on the bottom and then this lighter green layer on the top. And it's where the sulfuric acid, this is the sulfuric acid, where the sulfuric acid is meeting the iron 2 and the nitrate. And the H plus from the sulfuric acid reacts with nitrate, not reacts, but reacts with the nitrate to attack the iron 2, and it makes NO. And then the NO reacts with the iron 2 to make the brown ring. This is the brown ring. And so it's just a brown ring, which is a liquid layer. And so this tested positive for nitrate. So that's not very exciting because we got the exact same. I was hoping for something different. But let's go back to our, let's go back to this. Now take a look at how nicely coagulated our precipitate is. Do you see that? It's almost clear at the top. And so what I'm going to do is I'm going to test it with more HCl to see, if I can get some more precipitate. Because I got to make sure all the silver precipitated. And so let me get the HCl going here. And I'm going to watch this carefully. I want to see if I get more cloudy precipitate. If I get more cloudy precipitate, then that means I haven't precipitated out all my silver. And so I just see turbidity when it goes down. I don't see any more precipitate. So let me add a little bit more just to be sure. Again, it's not really turning cloudy. I'm just getting turbidity. Let me hit another spot. Okay, so I don't see any more cloud formation, white cloud. That means I precipitated out all the silver. Okay, the next step is I need to make sure I dissolve all the lead. Remember, the lead and the silver precipitate. In order to make sure all the lead is dissolved, I'm going to do this. I'm going to try to crush up the crystals to get as much of it to dissolve as possible. And to do that, I'm going to use a stir rod here. Let me rinse off the stir rod. Here, try it. Okay, so what I'm going to do is I'm going to stir it up now, and then make sure all the precipitate that can dissolve has dissolved. So I'm just crushing up the crystals, and I'm watching my fingers so I don't burn my fingers because it's quite hot. Okay, I'll let that go. While I let that go, I need to filter out the silver chloride. And so in this case, what I'm going to do is I'm going to dump the filter paper into the solid waste. Do that. I'm wearing gloves, so I'm tempted just to grab it. So I'm going to scoop out the filter paper. And then this time I'm going to wash the funnel. I'm going to wash it with a little soap. Let's see, how much time do I have? Rinse. Okay, now I'm ready to filter it. I'm going to filter it into this test tube here. So I'm going to transfer it from that test tube to this test tube. So in this test tube, I'm going to capture the filtrate in the bottom of this test tube and the precipitate in the funnel here. So let me set up another piece of filter paper. So just fold this again into a quarter. I don't bother turning off the end. Wet it down. Dump out excess water. And now I'm going to filter this. Here. Okay, so this time I'm going to grab this with some paper towel. Let me just crush it up a little bit more. We got to make sure any lead in here gets dissolved. Okay, now this filter rod is going to be wet with filtrate. I don't want to lose any ions, so I'm going to rinse the filter. I'm going to rinse the rod back in. I'm going to rinse off the rod, and so I don't lose any of the solution. So I'm going to rinse it back in there. Okay. Okay, now I'm going to filter this. Here. Pour this in here. Don't want to pour too much in because then it can go over the top. Here. You can see it's filtering pretty rapidly because the precipitate's stuck in the test tube. You can see it's stuck there. And so I'm going to tap out the precipitate out here. The test tube, it's stuck on the side wall. You probably can see it there. It's not coming out. Let me see if I can tap it a little bit harder. Oh, there it goes. Okay, I'm not going to bother getting every little bit of, there's a little bit of precipitate left in here, as long as I have enough to test. And so if you're looking down here, I have enough to test. There's plenty of white precipitate in there. I can see what's happening. But before I test that, I need to wash it off. Remember, we got to wash it. The first wash I'm going to collect in the test tube. And so that's my first wash. So I'm washing off the crystals. And I'm going to collect that here because that's going to be wet with filtrate. The second wash isn't going to be so much. And so this is kind of slow. Okay, there it goes. Okay, now the second and the third wash, I'm going to need one more beaker. Back here. Okay, now the second and third wash I'm going to do into waste. And the reason I need to make sure these are very clean crystals because we're going to test it with sodium hydroxide next. So I got the white precipitate. Okay, that's my second and the third wash there. Let it go. I'm going to turn off the bath since I don't have time to analyze another one. One thing you don't want to do is you don't want to let the hot water bath boil to dryness. If you let it boil to dryness, then that's going to cause problems. Okay, this is very slow to filter. So what I'm going to do is I'm going to just pour it off the top here to save time. These are little tricks one can do if they know what they're doing. Okay, there we go. Those crystals should be clean enough. Okay, then I'm going to get my sodium hydroxide, and let's see if these crystals turn black. If these crystals turn black, then that's positive for silver ion. Okay, so the crystals turn black. Do you see that? I didn't hit all of them, but I'm sure if I spray those top ones with some sodium hydroxide, they'll turn black too. There we go. Okay, so unknown A came out positive for silver ions. Okay, now let's test the filtrate. This is the filtrate here. The filtrate, let's scroll down here. So we got the black precipitate, so we're positive for silver. The filtrate should contain lead, barium, and manganese. And so the first step in analyzing the filtrate is we're going to add potassium iodide. So let me grab the potassium iodide. And see if we test positive for lead. Okay. So I add some squirts of Ki to this. Okay, that's 1, 2, 3 squirts and no precipitate, no yellow PPT. I might go for a 4th, but it seems like nothing's happening. And that was 3. Sometimes, things can happen, but it's looking like this one came out negative for lead. Well, that's fine because that means we don't have to filter it. And so now we're going to test for barium. Okay, so I don't do filtration here because there's nothing to filter. There's no precipitate. Maybe there is. Maybe there's a tiny bit of precipitate. Let's see. Let's cool it down. Maybe if I cooled it down. One way we can cool things down is by running tap water on the outside surface. When you cool things down, it makes them less soluble. So it was looking like it was getting a little bit cloudy. Maybe there is some lead in there. The other way of cooling it down is by using an ice water bath. It's a little bit hazy, you know, but we would expect more, although it's pretty dilute, considering how much HCl I added. All right, but anyway, let's check for barium ion next. We're going to check for barium ion by adding sodium bisulfate. So let's add some sodium bisulfate here. Let's see. Well, maybe there's a little bit. It definitely is getting a little bit cloudy, but we'd expect a little more. That's not enough to filter. Okay. Well, let's do something really quick here. I'm going to cool it down a little bit more. Okay, that's not really resounding. That could just be silver chloride that is precipitating out. Well, let's try the sodium bisulfate and see if we get any barium precipitate there. And I'm just going to do 2 squirts, otherwise it's going to get 2.5 squirts, too dilute. And nothing, no precipitate here. And so we got negative for lead, negative for barium. Okay, what's next? Well, what's next is manganese. So let's see if we have any manganese in there. So I'm going to add sodium hydroxide to this and see if we get a precipitate. So I got my sodium hydroxide here. Now I added a bunch of extra HCl in there. So I might have to add quite a bit of sodium hydroxide in here to see. So let me just pour it in here. Okay, this was not an exciting unknown. This unknown came out negative for manganese also. So this unknown only consisted of silver ions and nitrate. So this unknown was just silver nitrate solution. That was it. So that wasn't very exciting, unfortunately. And so that was unknown, A. So unfortunately, we're out of time, but since we're gonna skip exam 3. I want to do another unknown, I think, tomorrow, because you didn't see enough reactions. Since that wasn't the most exciting unknown, I was hoping for more. But we're pretty much we're close to out of time. So we have enough time to test unknown B for sulfate. And so let's go ahead and test unknown B for sulfate. That's a quick test. So the sulfate test for unknown B, I'm just going to use 1 squirt of unknown. And then I'm going to use a squirt of barium nitrate. Here. Okay, so nothing happened. So unknown B came out negative for sulfate. So unknown B only has nitrate so far. We're going to test unknown B for the cations next, but I think our cations are a bit simple, only having one cation. And so actually, we'll go ahead and do that right now. So I have unknown B here. I'm going to put in, so this had barium in there, a new test tube. Just have a small test tube again. So we'll do one. It says 12 milliliters for this, but you know, I'm going to go less than 12. 2. And then I'm going to adjust the amounts accordingly. 3. I'm going to go 6. Let's go half. 4. 5. 6. So I'm going to test half the size of the sample here. Rather than 12 squirts, I'll do 6 squirts. Okay, then let me get the HCl, and let's see if we get a precipitate here with HCl. And a precipitate would indicate silver and or lead. Okay, I got a precipitate here. This dropper is not working so great, so let me get a pipette. I got a lot of precipitate. Oops, you guys can't see that. I got to make sure I precipitate out everything like I just did. You know, we got to make sure we get all the silver out. Or this may be lead. I have a feeling this is the same. Hopefully unknown B is not the same thing as unknown A. That would be not very interesting. But we're out of time. And so once we do a couple of these, then it goes by pretty fast, I think. So what we'll do is we'll do a couple of these tomorrow at the start, and then we'll do lecture or after that. Okay, any questions? So there's going to be no exam for tomorrow, and then we'll throw everything in the final. And then this week we're going to have a nomenclature test. So if there's no other questions, we're out of time. So I'm going to stop the recording here, and I'll see you guys tomorrow.